right, so you may have heard, some of you came in fear because we're going to do proofs, but they're not like the proofs that you did in geometry. They're entirely different. And not only are they entirely different, but the format for the proofs that we're going to do are pretty much the same every time. The only thing that's going to change is the algebra that's involved in the second part of the proof. But the setup's going to be the same. Okay? So these kinds of proofs are usually for statements that have patterns involved, or so something like this. So if I have 1 plus 3 plus 5 and so on, meaning I'm adding odd numbers, right? In general, this would be the nth odd number. Meaning that the first odd number would be 1, we know that. The second odd number would be 3, everybody knows that, right? This little formula right here tells you what the last odd number is that you're going to sum. So if I told you to add the first 5 odd numbers, if you plug in 5 into here, 2 times 5 minus 1 is what?
9.
So that means you would stop at 9. You'd do 1 plus 3 plus 5 plus 7 plus 9. Figure that out. Does that make sense? Okay. Now, this would be what we call the long way to figure out a sum, where you actually add everything up. Okay? On the right-hand side is going to be what we call a shortcut. And right now, we don't need to know where the shortcut comes from, but we're told that it's just n squared. Okay? So we're going to kind of take a look at this and kind of explain where everything's coming from, and then hopefully that'll shed some light as to why we get n squared on the right-hand side, and then we'll talk about the format for the proof. Okay? So the idea here is that we're just finding the sum of the first n odd numbers. What is the first odd number? And if I stop, that's it. There's nothing to add except 1, right? But what if I add the first 2 odd numbers? So we get 4 here. If I add the first 3 odd numbers, what do we get? And let's just do one more for fun. What's this one going to be? 16. That is correct. So do you kind of see? This is the n equals 1 case. This is where n equals 2. This is where n equals 3. This is where n equals 4. Meaning on the left we have 1 odd number. Here we have 2 odds. Here we have the first 3. Here we have the first 4. On the right, what do you notice between 1 and 1, 2 and 4, 3 and 9, and 4 and 16? Yeah, if you square 4 or 3, I mean, that's exactly what this is telling us here. Do you guys see where they're getting that from?
Yes.
Okay. So the idea is that this works no matter how many odds we have. Okay? It's going to be your job to establish or prove that that works no matter what. Okay? And a proof by induction, let me write the format for the proof first, then I'll explain what each step kind of does as far as with an analogy. Okay? Okay, so format. There's 3 basic steps. Okay? The first step is called the basis step. And for this, all you're going to do is show that the statement is true when n equals 1. Basically, the first case. The second step is called the inductive step. Okay, and this is the part that's more involved. Okay, you're going to suppose that the statement is true when n equals k. And then you're going to show that the next case will also work. So you're going to show that the statement is also true for n equals k plus 1, which is the next case. If we're starting at k, with assuming that up through k works, k plus 1 would be the next logical case. The third step is the conclusion. No, it's very simple. The conclusion is basically restating the statement, and you just explain that it works by induction. Okay. So these are going to be some weird analogies, but hopefully you guys kind of buy it, and then we'll do the math behind it. All right. If you're like most people, when you're going swimming, whether it's in the lake or in the pool, what do you do first? Jump right in? Change. Okay. Let's say you're ready to swim, Colin.
Jump right in, test the water.
Test the water. How many of you have done that before? Where you just kind of feel around to see how cold or warm it is, right? Okay. That's essentially what your basis step is. Your basis step is a way for you to see, okay, I want to make sure that this actually makes sense. So I'm just going to test the first and most simple case. If the first and most simple case works, then I'll get a little bit more involved with what I'm going to do. If it doesn't work, then obviously we've established that this is something that we're not going to prove because it doesn't make any sense. Okay, so that's basically getting your feet wet, just testing the waters. Okay, I like that. The inductive step. Okay, so this is the part that's kind of tricky to understand, but I'll show you a visual analogy.
Nice.
Have any of you ever played with dominoes before? How many of you have set them all up and then knocked them down just to see them all fall? Okay, so here's what this means. Okay, if you have, and this is going to be a horrible example of dominoes, but pretend these little lines are side views of dominoes, right? And you knock that first one over, right? Well, what's that next one going to do? Knock the next one down, and so on and so forth, right? The basis step is essentially knocking the first domino down, okay? So now here's what the inductive step means. The inductive step means that somewhere along the line, now we have k dominoes, okay? And we're supposing that up through k works. What that means with the domino analogy is basically that all k dominoes so far they're all knocked over, okay? What we're trying to do, let's see if I can get a different color here. Perfect. What we're trying to do is check whether or not this is going to happen. So if the first k dominoes are falling over, does that necessarily mean that the one after that is also going to fall over? That's what it means here. And maybe not, but if we can prove that these k dominoes falling over implies that the next one's going to fall over, that basically proves that this works all the time. The reason is because k is arbitrary. K can be any number. So we could have a string of 1,000,000 dominoes, and if we say that 1,000,000 dominoes are falling over and the 1,000,001st domino is going to also fall over, do you guys see the power in saying that? That no matter what, all the dominoes are going to fall? Because k can be any number we want it to be. You guys kind of buy that? Okay. So that's basically what's going on. All right. And if you can show that every single case works, you've basically said, okay, that's induction. We've shown every case is going to work. So now we just go on to the conclusion and say, bless you. Here's how everything's going to work. Okay? All right, so let's revisit This is a very simple example to follow because we all understand here we're adding odd numbers, and the shortcut would be to just figure out how many odds I'm adding and square it, right? So the long way, if I said, hey, add the first 10 odds, you would do 1, 3, 5, 7, 9, 11, and so on. Add them all up. Or the shortcut would be to do what? 10 squared, and you get 100. We're trying to prove that we're allowed to do that. That's going to work. Okay? So let's formally write this example down. So we want to prove that 1 plus 3 plus 5, etc., through 2n minus 1, that's always going to be n squared. Okay? So I'll go slow.
How much room are we
A lot. For me, it takes about a half page, so I don't know, depending on how big you write. Let me see how big you write.
I'll write smaller.
You can fit it in there.
Okay.
Yeah. Okay, so first is the basis step. And I'm going to expect you guys to write what you're doing because it'll remind you what you're supposed to do at each step along the way. First, we're going to show that the first case is true, right? That the statement is true when n equals 1. Okay, so now I'm going to utilize the abbreviation left-hand side, LHS. If I'm simply doing the first odd and finding the sum of the first odd, what would that sum be? Yes, very good. On the right-hand side, not that you would, but the other option is to take however many odds you got, which in this case is 1, and square it, and the result is 1. So we've established that this pattern works at least for the first case. Does that make sense? Left-hand side is right here, right? Left-hand side, right-hand side. Okay? All right, so the next step is the inductive step. This is the one that tricks people up sometimes, but we'll go through it nice and slow so that you guys see all the different necessary pieces. So, and I'm going to use the verbiage that we used in the format when we explained it. So we're going to suppose that, and I'll just rewrite the statement now, that this is true when n equals k. If n equals k, then my statement turns into 1 plus 3 plus 5 plus etc. plus 2k minus 1 equals k squared. Okay? What we need to show is that if this is given to us, in other words, the first k dominoes have fallen, we're going to show that the next domino or the next case must also work. So that means that not only am I going to add the first k odds, so 1, let me write this down here, 1 plus 3 plus 5 plus blah, 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 2k minus 1. So this would be your first k odds. We just need to go one more odd after that. So if I'm going to go up to k plus 1, that means that right here where I have the n, instead of replacing it with k, which is how I got this statement, I'm going to replace this n with k plus 1. What's that? Yes, it does matter, because that's the inductive step. We suppose that the statement we suppose that the statement works or is true when n equals k. Here's a good way to think about it. N represents the end of the string of numbers. Okay? K can be any number. Does that make sense? So that's what we say, all right, let's pretend n is k. If n is k and that works, then this statement needs to be true. Okay? And the thing we're trying to do now is, with this being true, does that imply that the next case is also true? So that means I've taken the first odd, the second odd, the third odd, up through the kth odd, which would be 2k minus 1. And now this right here would be the k plus first odd. That's just the next number in the sequence. Okay? And if that works, on the right-hand side, instead of k squared, what should I get? I should get k plus 1 squared. Because my formula up here tells me that however many odds I have, I'm just going to take that and square it, right? So if I have k plus 1 odds that I'm adding now, I'm going to have to do k plus 1 squared to figure out that sum. Okay? So now, this right here, this whole thing, this is what we call the inductive hypothesis. I take that back. This is what we call the inductive hypothesis right here. We are going to use the inductive hypothesis in this giant equation. And it's going to make life a whole lot easier in a minute. Okay? So if I start on the left-hand side, so just looking at the left-hand side, what do I know about the first k odds? Do I know what that adds up to? Look at your inductive hypothesis for a hint. What does 1 plus 3 plus 5, etc., plus 2k minus 1 going to add up to? To k squared. So what we're going to do is just one big old-fashioned substitution here. The left-hand side, so right here, that becomes k squared. Because that's what the inductive hypothesis tells us. Do you guys see that? Okay. Have I done anything with the next piece yet? So this is just going to come right on down. And now the hard part is over. You're just going to multiply this out, and let's see what happens. So we got k squared plus 2k plus 2 minus 1, which is the same as k squared plus 2k plus 1. And if this works, what should I get? I should get the right-hand side. Do I? I sure do. So this is what the algebra looks like. You start on the left-hand side. You use the inductive hypothesis to replace it algebraically. You take the next piece, the next term, whatever it looks like, put it in there, do some algebra, simplify, and then turn it into the right side if possible. If you can make it turn into the right side, then we're done basically. If you can't, which is not going to happen for you guys, you probably made a mistake somewhere. You're never going to be asked to prove something that does not work. Okay? So if you're not getting it to work out, chances are you made a mistake somewhere. Okay? So we're on now to step 3, which is the conclusion. In the conclusion, you're just going to rewrite the original statement because we've established from this inductive step now that 1 plus 3 plus 5 plus 2n minus 1 definitely is n squared by induction. Okay. Are there any questions on that? Thank you. Are you sure? I have one more to do today, yeah. And that's it. This is for you. Uh-huh. And then, what are you doing 9th today? So, tomorrow, test? Okay. All right. So, last example. Does everybody have this down? Okay. Prove 2 cubed plus 4 cubed plus 6 cubed, etc. is going to equal 2n squared times n plus 1 squared. So here we're essentially adding even cubes. 2 cubed, 4 cubed, 6 cubed, and so on. The shortcut says, instead of adding them all up by hand, if I wanted to do 20 even cubes, then I would just do 2 times 20 squared times 20 plus 1 squared, and that'd be the answer. Okay? All right, so to prove it, what's the first step? And in that basis step, all we're doing is proving that the first case works, right? So for n equals 1, the left-hand side would be what? 2 cubed, which is 8. So all I'm doing is taking the first term, getting 8. The right-hand side, I should be able to plug 1 directly into this formula over here, which would be 2 times 1 squared times 1 plus 1 squared. I get 2 times 1 times 4, and sure enough, we get 8 either way. Okay? The inductive step comes next. Suppose what? Suppose that when n equals k, this is true.
Yeah.
So how do I write that? Basically, yeah, swap out the n with k. So suppose 2 cubed plus 4 cubed plus 6 cubed, etc. plus 2k cubed equals 2k squared times k plus 1 squared. We will prove what? So we're going to add the next number in the pattern. So we will prove that 2 cubed plus 4 cubed plus 6 cubed still got to include 2k cubed, bless you. But now we're going to go ahead and add in, if I were to replace n with k plus 1, that becomes 2 times k plus 1, but all of that gets cubed. So all I've done is replace the n with k plus 1. Okay? On the right-hand side, I probably should write a little smaller. I do the same thing. All my n's, or in this case k's, become k plus 1's. So instead of k squared, it's going to be k plus 1 squared. Instead of just k plus 1, this k becomes k plus 1, which is k plus 2 squared. Okay? So, let's see what happens. This is where we use the inductive hypothesis, which is right here. On the left-hand side, do you see that copied anywhere?
Yeah.
What's this first box going to turn into? 2k
Or 2k.
squared, very good, times k plus 1 squared. Bring down the next term, because I haven't done anything with that yet. Okay, and our job is to take this left-hand side, which we've currently replaced a lot of it with the induction hypothesis step, and turn it into the right side. You see how on the right side everything's factored? So a good idea here would be to probably factor it. So don't bother multiplying this out. You know what I mean? Because it's already factored a little bit. What can we do? Do you see anything in common?
2.
You can take a 2 out. What else?
K plus 1.
A k plus 1 squared comes out 2, right? So 2 k plus 1 squared gets pulled out as a GCF. And now what's left? This k squared is left. So that gets written down. Plus, here I took out the 2. And I took out 2 out of 3 of these. So that leaves us with just k plus 1. Technically, it's to the first power, but it's still there. You don't need to, yeah. But just so that's clear. Oh. Something, I totally messed something up. Did you guys see it yet?
K squared plus 1.
Right here, when I wrote this box, this kind of covered up this parentheses that says everything is cubed. Do you guys see what I'm talking about? Let's fix that. So this is all cubed. So now we can fix this real easily. Since this is all cubed, I took a 2 out, right? This is really an 8, right? So what should this be on the outside here? That should be a 4. Okay? Do you guys see that we're getting pretty close here? The 2 is there, the k plus 1 squared is there. Somehow we're supposed to get k plus 2 squared out of this. Well, if you distribute the 4, is that how it factors? Sure is. And that is the right-hand side. Okay? So in the last step is the conclusion, which is basically restating what we were trying to prove. 2 cubed plus 4 cubed plus 6 cubed, etc., plus 2n quantity cubed does in fact equal 2n squared times n plus 1 squared by induction. Okay. Any questions on that? Why what?